Well, hello, Earth-Space Sciences class. We're attempting to do the first part of the plate tectonics lecture, actually most of it. The part in your on your Moodle page entitled Layers of the Earth. So if you look at Moodle, we're right here. So we're under plate tectonics. Actually, that's the label of of your notes. So plate tectonics, and the notes that you're looking at would be right here. So this is where we're going today. We'll actually get through a part of, hopefully most of this. And so we're going to look at our world. And so if you look at Google Earth, which I will use quite a lot, we'll come back to that image, and we zoom way out, it's easy to see and think of our Earth as a giant sphere floating in space. It's kind of interesting when you consider the incredible weight that the Earth must have, that we are in fact floating in space. Okay, and so there's a good image to have. And so we're going to start with a journey to the center of the Earth, from sort of outer space to the middle of our world, to steal a title from an oft remade movie, Journey to the Center of the Earth. If you look at your notes, I want to just start off a consideration of our atmosphere, which is the gaseous layer surrounding our Earth. We're going to talk about atmospheres of other celestial bodies too, but we're going to start off with our own. And if you think about it, it's what you're, some of what you're breathing. And right now, you're breathing actually mostly nitrogen. About 78% of what you're currently breathing in is nitrogen. It's just you breathe it right back out. You don't really benefit from that at all. 21% of what you're breathing is oxygen, 1% other. I should just pause right here, folks. I'm having a little trouble with the microphone on this. I know it's going to be sounding a little scratchy. Working on it, but I can't do anything about it right now. So hopefully it'll be okay for this video. And so back to the Earth. And if you asked your class of elementary kids how far up outer space starts, I wonder what they would say. I wonder what you would say. If you think about how far from Earth would you have to jump up into space before you get to outer space? Well, this diagram hopefully helps us think about it. And so out here we have the outermost layer that anybody would call having our atmosphere, and that's called the exosphere. And if you look here, it's 190,000 kilometers out. Now, 1 kilometer is about 2/3 of a mile, just to give you an idea of the distance involved there. So a long way out. And this is really defined as where light atoms are pulled back by gravitational pull to Earth rather than just being allowed to freely wander out into space. That's what would define that outermost layer of our exosphere. Probably more commonly, outer space is defined as anything beyond the Kármán line. Now, the Kármán line is a line above which flight cannot happen. You have to have a rocket to go beyond the Kármán line. There's not enough atmosphere to create lift. As air flows over either side of a wing, it flows farther over one side than another. It creates lift, and that allows planes to fly. Above the Kármán line, there is not enough atmosphere to allow that to happen. And so a lot of people will consider the Kármán line, probably most commonly, the Kármán line is thought of as outer space. Beyond the Kármán line is outer space. And it is 100 kilometers up, about 65, 70 miles up from our surface, you'll find the Kármán line. It exists within a layer called the thermosphere. Another question, if you ask your kids, what is it like when you go farther and farther away from Earth's surface? My guess is that them, and probably you, that experience will have been with going up on a mountain. And you know that as you go up a mountain, it gets cooler. In fact, if you go up a mountain like, let's say Pikes Peak outside of Colorado Springs, Colorado, it might be 80, 90 degrees at the base. It might be 50-some degrees up at the top of Pikes Peak. And so that will be their exposure. But that's all occurring in the troposphere. And if you think about it, we're actually, in daytime anyway, getting closer to the heat source, the sun. So why would we be getting cooler as we get up higher? And in fact, in some of these layers, you actually get warmer as you go through them. In fact, astronauts, that's a major concern, that they have too much heat, or cool if it's on that side of the Earth that they're at. So, yeah. So we're thinking about that layer, the thermosphere, and in the thermosphere, the temperature actually rises because there's very little gas as you go from the base of the thermosphere towards the top of it. Now, not mentioned here is the ionosphere, and it exists kind of at the base of the thermosphere between the mesosphere and the thermosphere. And like its name suggests, it's a layer that has lots of ions. If you remember that term from chemistry, an ion is an atom with a charge, a plus or minus charge. And there are lots of them in this layer. And the reason I bring that up is because if you've ever had a cell phone call dropped or a TV or radio signal interrupted, it could be because there's lots of energy in the ionosphere, and that has scrambled that signal that comes from Earth, and it has to get to these satellites that are up here in the thermosphere. Okay, if it can't get through the ionosphere cleanly, it might not get to the satellite or back to Earth, and your cell phone call gets dropped. So the ionosphere, while it's not on here, is something that impacts us. The mesosphere, I'm not going to say too much about it. Temperature falls as you go from the bottom towards the top, kind of like the troposphere. There's a layer of solid Earth with that same name, and I'm not going to complicate things by talking too much about this one. The stratosphere and the troposphere I am going to talk a little more about. Stratosphere is a layer that has a couple of key features in it. The jet stream and the ozone layer. Now, the temperature in the stratosphere does actually rise as you go from the base towards the top of the stratosphere because we're getting towards the sun, closer to the sun, kind of different from the troposphere. Now, if you think about if you've been in a jet recently and you've heard that pilot come over the radio and trying to tell you how high you're flying, you might have heard the number 25, 30, 35,000 feet, maybe even more. And if you ever wonder about why they got to go up that high, why they go way up here and then come back down, why can't they just scoot up 500 feet, scoot across the surface, and come back down? Well, part of it, there's a great circle distance explanation that I'll leave to the physicist. But part of the explanation we can handle here is the existence of jet stream winds. Now, jet stream winds are 100, 200 mile an hour winds. And wouldn't it be nice if you went up in a jet, got a 200 mile an hour tailwind, and you'd get somewhere quick and with burning less fuel? And so that's in actuality what's going on. This ozone layer is also there. You probably heard a lot about the ozone hole when you were younger, and maybe not as much about it now. You see, the stratosphere is thin over the poles, and in that stratosphere is the ozone layer, which ozone we don't want down at the surface. It's an air pollution, but up in the stratosphere it helps keep excess amount of solar radiation from getting through the Earth. Well, there's always been a hole here over Antarctica, but our use of refrigerants in air conditioning and other places have expanded that hole. Well, they expanded it, we switched our refrigerants, and now it's shrinking. So you don't hear so much about it anymore, which is really a good thing, but that's why. Okay, and then stratosphere has the ozone layer and jet stream winds. I just wanted to look here. I think there was another picture that I would like to show you if I can find it. And it's evidence that the stratosphere exists. Yeah, right here. And you've all seen it, potentially anyway. This is a thunder... well, that's actually a pyrocumulus cloud. Here's a thunderhead. You've seen them from Earth. And that anvil-shaped top that we're familiar with, I guess that'll work fine. Here, this cloud has risen up so high, it's penetrated through the troposphere and into the stratosphere, and the jet stream winds have sheared that top off and skewed it in a particular direction. And so when you look at a big thunderhead and you see this flat top, there you're actually seeing visual evidence that the stratosphere exists. Okay, and then the troposphere, the layer in which most of Earth's water vapor and weather exists. Okay, if you hit Earth's surface, then of course you're more likely to hit water than land. About 2/3 of Earth's surface is water, and about 1/3 is land. And to hopefully help make that case, oops, this is a picture that might help visualize that. So here's the amount of land surface that's above sea level, and here's the amount that's below sea level, and so we'll start with that. And so most water is ocean water, seawater, 97.5% or so. So only 2 or 3% is actually fresh water. And if you look at the amount that's fresh water, this is a diagram that attempts to show that. So here's salt water, and this little pie slice here is fresh water. That actually looks like more than 3% to me, but that's all. It shouldn't even be that much. And so if we look at that little bit of all of Earth's water that's actually fresh water, most of it is not even surface water. Most of it is groundwater or ice caps and glaciers. Well, I guess that's surface water of a frozen sort. Only this tiny portion here of all of fresh water is actually lakes and streams and swamps. But water flowing through rivers and through the atmosphere, I would argue, makes up most of the sculpting tool that God uses to make Earth's surface look like it does. And so here's another look at it, and this one actually includes water vapor right here and soil moisture. So here's all fresh water. That little piece there is, this is all water. That little piece is fresh water. So here's ice caps and groundwater. This little piece here is lakes, rivers, water vapor, and soil moisture. I hope you find that incredible, because I do. That's just a lot of Earth's water is salt water. Not much is fresh water, and it's that fresh water that we depend on so much. Okay, the biosphere, the layer in which life exists. I'll make the case that life does impact rock. You know, if you think about picking up, we're going to go to Wang's, Minnesota for our field trip and collect fossils, and so those are actually parts of a rock. You've probably are familiar with coal, and so coal is made up of things that used to be alive. We know about the effect of beavers on landscape, and so right here I want to show you another effect of something living, that being humanity, on Earth's surface. So you see this little dot right here. Oops, I didn't want to do that. There we go. Okay, there's a little dot right here above the fingers, little white dot right there. This is Great Salt Lake. Okay, Provo, Utah would be here. Great Salt Lake City be up here. So if we zoom in on that little dot, we're going to see it's actually a human-made feature. It's actually a mine. So humanity has carved Earth's surface, and if we look at this, it's a pretty incredible hole in the ground, folks. Google Earth gives us a nice perspective. If we go way down on the bottom, you can see some of the drag lines and stuff. If you put the cursor, if you look down the bottom, it'll tell you the elevation right here. Down here we're 4,650 feet above sea level. That's still pretty high up in the air. We're only 900 or so here. And the top is 7,700. So, you know, we're basically 2/3 of a mile from the top to the bottom. And if you measure this from one side to the other, we're basically 4 miles one side to the other. That's a pretty big hole in the ground that humanity has created. And so the biosphere does definitely impact Earth in lots of ways. Okay, next thing we're going to do then is look at this picture right here. We've hit the surface of the Earth, probably splashed, might have splatted. But now we want to go on our journey from the surface to the center. Not a journey any of us would want to make. I'll make that point right now. But if you look at it, you know, we're just a little shy of 4,000 miles, 6,370 kilometers from the surface to the center. So Earth is a little less than 8,000 miles in diameter. And so as we're going on our journey to the center, then we want to look at features and try to come up with a theory that explains those features. And so here, this little box right here, this little portion of Earth's surface has been blown up right here. And here we have oceanic crust, and beneath it the lithosphere. Folks, this is the only solid portion of the Earth right here. So from this little light tan and black line, you are truly living on an eggshell. We are all truly living on an eggshell. This is hard. Beneath here, the asthenosphere, this is soft. And so we would call this top part here the crust. And we can see that it's broken up into two parts. Crust which lies under an ocean and crust which is high and dry. Now, folks, you gotta realize we're making a decision here. We're not calling the surface of the ocean Earth's surface. We're calling the hard rock underneath the ocean's surface Earth's surface. Okay? So the water, because it can ebb and flow, we're not saying that's the surface. It's that hard rock under it. So we're going to look at this crust right here. And when we look at that crust, we see some features to it. If you look at the rock, with that dark rock, what makes it up, we see that it tends to be thinner. Yeah, this ocean crust is thinner than this continental crust. It tends to be younger. If we radiometrically date this rock, it tends to be younger. It tends to be denser, heavier, just really compressed rock. And it tends to be made of a kind of rock called basalt, which may not mean a lot to you now, but it will shortly in the future. Now, until recently, and I mean, I'm talking my lifespan, so maybe not that recently for you guys, people thought that you would simply go in the ocean at California, and if you could hold your breath really, really good, you would walk across the ocean floor from California, and if I zoom way out, you would simply then keep walking all the way across until you came to Japan here. Sorry, I kind of had to move it just a little bit. I don't know if I can get them both on the map at the same time. So from the west coast of the United States across here to Japan, and you'd just be walking across this flat, basically swimming pool bottom. It wasn't until, well, post-World War II, when sonar imaging was developed, that people started to look at the ocean floor. And a couple of people named Tharp and Heesen, Marie Tharp and Bruce Heesen, looked at that ocean floor and discovered that, in fact, it wasn't just flat. There were features there. And those features would include the list that you see in your notes. Number one is a mid-ocean ridge. So again, just to show you where we're at in our notes. Okay, right here, oceanic features, main features, mid-ocean ridge. And so if we look then at Moodle, right here, I have a video that I want you just to pause this video, click on that one, open it up, Mid-Atlantic Ridge video. It's only 1minute 22 seconds long. Take a peek at that, and it will show you some characteristics of the mid-ocean ridge. Okay, I'll just pause here and let you watch that. And hopefully you can just break, because I'm going to keep on going. The next feature in your list is a trench. And again, there's another video clip right here, the Marianas Trench, which looks at a feature of the ocean that we find right here. This is the Marianas Trench. Here are the Philippines, here's Taiwan, here's Japan. And this is an incredible video. And this is the deepest point known on Earth's surface. So if you're in a rowboat on the ocean surface here, you flip a nickel overboard, it'll fall for better part of a day before it hits the bottom of the ocean at the Marianas Trench. This video clip is about the first two people to actually descend to that depth, and it's incredible to hear their story. One of them, Don Walsh, is still alive, and he's narrating some of this, so I'll stop here and let you listen to that. Okay, hopefully you've gotten through that video. I just find it incredible that those two gentlemen are descending and the glass window pane actually cracks and still they go down. If that was me, I'm going, get me out of here. You know, if that crack had gone all the way through, as he said, they would have been instantly dead. There's thousands of pounds of pressure on the water. It would have shot through that submersible, cut it in half, flattened it, and they would have been truly instantly dead. There are other features. There is a broad sort of featureless portion of the ocean called the abyss. There are seamounts like Hawaii here. The island of Hawaii is a seamount. If you look around here from its base to its summit, Hawaii is the tallest mountain on Earth, well taller than Mount Everest. It's like 34,000 feet tall. You can actually snow ski some days on the summit of Mauna Loa right here, which is 13,000 feet, and then go surfing down here in the ocean if you wanted to. So that's a seamount. And lastly, I have listed there, I'm not going to say much about it, continental margins. And if I zoom out here, continental margins are this part of the ocean crust right here that's light blue. And that's a part of the ocean that's actually physically connected to the continent here, but because it's flooded by seawater, we call it an ocean feature. So anyway, we'll move on from that. So again, in your notes, we're right here, we've gone through these, and now we're going to look at continental crustal features. And so, you know, not as much of Earth's surface. So if we go back to Google Earth, and if I move this cursor, you can see that that Pacific Ocean is huge, and the Atlantic isn't as big, but boy, there's a lot more water on Earth than there is solid. And so, what is it about a landmass that makes it a continent? Well, there are some features like folded mountain belt, like the Rocky Mountains right here, the Sierra Nevada Mountains here, the Appalachians here. Those are all folded mountain belts. Folded means the rocks have been twisted and contorted, folded, if you will. There's also something called a craton. If you've ever gone into the boundary waters, is part of what's called the Canadian Shield region of our continent. It's about like this. And that shield region is typified by a particular kind of rock that makes the boundary waters really, really pretty. It's these old, contorted, weathered, igneous, which are rocks formed as magma cooled, and metamorphic, rocks formed by heat and pressure. That's typical of what we find in the shield region of our continent. Okay, that's what you see in the boundary waters. And then also, if I go back here to Google Earth, and we go to Taylor's Falls, there's a stable platform region of a continent. And that's where those older shield rocks are covered by younger sedimentary rocks. Sedimentary rocks are rocks made of pieces or parts of other rock. And very typical if you've gone into Taylor's Falls to go to Interstate Park and you're on Highway 8 here, and you just come over the cliff edge right here and you start to drop down. And if you look at the side of the road there, the rock that you see, that's sedimentary rock. And it tends to be made of the older sort of buff-colored, light tan-colored rock, often in layers. That's what we find overlying the shield. That's the stable platform, which interestingly enough, we're at the margin of. This layer of sedimentary rock runs out just north of the cities, maybe 100 miles, and all you see beyond there is this older shield rock. Okay, if we go back to this picture here, then we have gone through the topmost layers of rock, these crust, oceanic crust and continental crust. And then if you look in your notes, the next layer is the upper mantle or asthenosphere. So that would be this layer of rock right here. This rock is like Play-Doh. Heat has won the battle here. Now really, as we go to the center of the Earth, the thing to remember is this. As temperature dominates a layer of rock, it'll tend to be more liquid. As pressure dominates a layer of rock, it'll tend to be more solid. Because as pressure increases, liquids solidify. As temperature increases, solids liquefy. Okay, so temperature has won the battle right here, and it has made this rock, maybe it's not exactly accurate to call it a liquid, but it is capable of movement. It is like Play-Doh. Okay, and that's a key thing to remember. Along with those oceanic and continental crust features, I got to come up with a theory to explain them, because like mid-ocean ridge, trenches, volcanoes, they're all geologically active. It means there's volcanoes, there's earthquakes by them, things are happening. In the asthenosphere, part of the answer is going to be the nature of the asthenosphere. It's like Play-Doh, it's able to move. Underneath it, the lower mantle is solid rock. It's here, pressure has won the battle. These overlying layers are squeezing so hard on this that it now becomes solid. As we go a little deeper, temperature wins the battle again. And the outer core is liquid because it's so hot there. But then you go to the inner core, and this whole layer here is pushing down on it. And even though the heat source is right here, this is solid because of the incredible pressure on it. Now the heat at the center would probably be from remnant heat from creation, as well as radioactive reactions going on, give us this furnace, if you will, at the middle of our Earth. Now it's important to realize this. Later on we're going to talk about Earth's magnetic field being generated because this liquid core is moving around that inner core. Okay, so with that I'm going to stop, and I'm going to do just a few notes at the start of class on continental drift and plate tectonics, which is an attempt to answer why those features, oceanic, continental, why they are where they are, why they behave like they behave. And have a good day. I'll talk to you tomorrow.